and nice to meet you to this new episode of WeekBit. This is the assembly part 1-2 and or hashtag 2. And here we have the AVR studio from the ATMEL studio from Microchip. Is very funny. The company bought that other ATMEL company, and we have our program here, that little program what I'm writing ago. This is the assembly code here. You can see, you remember it, but it's not white on black. It's black on white. And now we would like to build this solution and say build solution, and we have success. You can see that here is 1 success, or up to date, 0 failed and 0 skip. I'm wondering, that's so clean. Now we want to also use this chip. This was the wrong chip, but we have here a chip one that we can program in the part. Anyways, I don't know how was the word of this programmer. USB tiny simple programmer, maybe this from GitHub. It's a USB Basam. This, I think this is it. Oh, swoop, swoop, swoop. And now we must have a watch on the controller. Now we see in the oscilloscope and the port C number 5. We remember the bit 5 is the OSCI bit, and here is the oscilloscope. It's a small one oscilloscope, and you see here a needle in the middle. Very funny. If I change the time base, it's I can show you the needle, but if I do it to milliseconds, you see sometimes it doesn't synchronize, but it flashed sometimes 2 needles in these 10 milliseconds on it, but we can measure 1. And look here. It's super. We do the measure range, how long these bits need. Measure range cursor. We change the cursor to AB. Should we do that? No. The voltage? No. We would like to time. The time is important for us, and so we measure the time for A. I go with the A mark here to this falling edge, and I'm on it, and with the B to this falling edge here, to this rising edge. Yeah? It's a rising edge, and we see it's in time 656 nanoseconds. Yep. Interest. 656 nanoseconds is the nop. Yeah. That means here in this timing, before the falling, before the signal is falling, here we have the command clear bit immediate and or clear bit in register. Here we have that, I don't remember exactly, clear bit, and we clear it, and it's falling down. And then the measure, we can switch this off. None with none. Look, here's the signal. Come on, super. Here we have the grid, and the grid is changing to Blinky, and we're writing here Blinky assembler, and the date is the date is the 11th of April. The things are here, and I show you, we go to the point where we should know what's happened. the first part of all here is the declaration. Yep, it's declaring the boards, the registers, and the bits of the LEDs and so on. And we say here, OSTI bit number 4 is the blue LED. Okay, we checking the 4, or what do you want for color? And here are the timers and so on. I would like to tell you now again what's happened here. The program starts after reset is the program counter 000. It's a 16-bit address, and the address is 16-bit. 16-bit address, and it starts here. Program starts here. We make here a line that you can understand it. This starts here at 0, and the important thing is that we jump to the reset vector, and the reset vector is later. It's later, and here is the reset vector. And the address is 100 inside the flash memory where the program is stored. It's 100, and then we put the stack pointer on the back side of the RAM end, because the stack pointer is running from the run end till the 0 address. Then we initializing the boards. Data direction register for B and port B. All the things are standing. Never write here a number in. You must also name it. If you change something, a number, then you change it here in the declaration, and not in the program. The program are only with words. For test, you can also this is normal. You can also name this, but okay, the 3 addresses. This is normal. Then the program is running in the initialization. It's running here around. Running. Came to the status, running, initializing the timer and the interrupt registers and so on. And important, initializing this this SI. This is the enable. This is the enable for the interrupt. It's a global enable. And then initializing the sleep, this SMCR register, and then going to sleep. After the timer 2 is running over, it makes an interrupt and jump here to this interrupt register. Here. R jump timer 2, compare A, handler. This is a hard-coded address. It's in the list of all the vectors where the interrupt vectors are B. I would like to show you this in that case that we have here the interrupt. Where are the interrupts? Here are the interrupts. Here you have the interrupts on page number 40, page number 49. Would like to write this here. Interrupt registers, page 49. It's a list here. So then it jumps to the handler, and what it's doing here. This is the first clear bit what we see in the oscilloscope. Clear bit is the falling signal. Then no operation needs time, no operation needs time. All this operation needs exactly this time. It's 1 divided by 8 megahertz. It's 125 nanoseconds. This need one cycle, yeah, at the 8 megahertz. And then after this time, we remember we have 656 nanoseconds. That could be. In case of that, we have 656 nanoseconds minus 125 minus 125 minus 125. These are the knobs. Is how much? 281. That means the set bit needs 281, because after the clear bit immediate signal it's the falling signal. It's the time you cannot see from the start to the end. That means the set bit needs 281 nanoseconds. Maybe this is divided by 25. It's crazy. It's 2.5. Maybe we measure it wrong or stuff. It could be wrong. Maybe the processor is too fast. So, and now came the important thing. Here is the control. Yeah. And here you write all your programs what you want to run for the future. The grid is the starter kit for your assembly on 328. And we say here now, we got a R call, and we say Blinky. We jump to Blinky. Yes. Where is Blinky? All 10 milliseconds around, the Blinky will be wake up and check up what's happened. We go now back to the end of the program. Make here a line. We make here a dot comma, and inside this is the grid. You do nothing inside this anymore. You don't analyze it. You don't. What's also important, you can change the 10 milliseconds also if you change here the registers for the speed. Here is one of the speed, and the calculation is here. Yeah, you can do it to 5 nanoseconds, 5 milliseconds. You're doing this by half. You can change this here, the speed. But 10 milliseconds is a good timing. So, we're leveling here Blinky. And the first thing what we're gonna do is we compare the counter register from the Blinky. We set a LED or we close it. Should we set it or should we close it? That means we must enable it or we clear it. That means we must count the time here. All 10 milliseconds will be Blinky come. Yeah, it comes again, all 10 milliseconds. And if we said we need a half second, that means a half second is 500 milliseconds divided by 10 milliseconds is 5 times, it's 50, and 50 times 50 times. 50 times means for a half second. We can do that. We can do that with 300 milliseconds. It's also good. Viewable. It's 30 times. Okay. We would like to have a Blinky with 300 milliseconds. And the thing is that we can also program is the LED longer on or is the LED longer off. That means we would like to say the Blinky time is here. You can say Blinky counter. Here is counter is with the Blinky. And what is the Blinky? Numbers and names. We put it here. We say AQ Blinky time is, we can also use it at decimal number 30, but it's not so cool. We say it's a decimal, we say 30, 1e, we say 1e, 0x 1e, 300 milliseconds is 30 is 1e. LED timing, we can write here something here, Blinky time, and we must think, should we count up or count down? We make a countdown and we load in the counter the Blinky time in the initialization before the timer. Here is the Blinky time. We can say init Blinky time. We say init Blinky time, and now, oh, it's not here. I'm sorry, it's not here, it's in the program. Reset vector, here status timer. Say here init Blinky time, and we say as follows: move or load immediate. Sorry, load immediate is a number. Load immediate counter with Blinky time. Load with 300 milliseconds. Okay. Then we check up here. The first what we check up here is the timer counter 0? We say compare immediate counter with null. This compare counter with null. Okay. Oh, you can see. And now what we can say, branch, if it's equal to Blinky, change, to Blinky change, sorry, okay. If counter is 0, then jump to Blinky change. Okay. We go here, Blinky other line change, double point, and now we would like to check. We check up, is it a number? Is it a Blinky change? If it's set, we would like to clear it, and if it's clear, we would like to set it. So this is a bit command. We can watch in the bit command, and I must have a watch myself. In case of that, I don't program so much in assembly. It's for me falling out. I can compare a bit. This is not a problem, but now I must have a watch. So I inform me in the internet on the list. It's a skip with bit is set or skip with bit is clear, and skip if bit is clear in register in port. What was this port where the LED is switched on? It was port C, and the thing is port C. Port C number what? I don't remember it. But what I found out is this, the information for the assembly code, you can read it here. What is now? What is now? You can read it here. I must insert it here. Insert it. If you search this, there you have the instruction set. Here is the instruction set. And instruction set for the assembly. ATMega328P assembly. Yeah, this is a. And this PDF, there is skip if bit is clear, and I would like to do that import C, but which number I don't remember. I must have a search. which bit we skip. If we skip, this is jumping over the next one. Yeah. If it's clear, then we change it to high. Yeah. We change it to high and reload the counter. I don't remember doing here a question mark now. We jump then skip if bit over, and here we say jump to the Blinky LED on off. Okay, that means Blinky LED on, and now we do this here. Set bit immediate import C question mark. I don't remember what it was, the LED, what the number was, and or is it in register? Don't remember it. It's in register bit. It's bit. It's bit LED red or bit red LED. I don't remember. I must go back. What is bit red LED? Is the 0 one, or should we take the blue one or the red one? We take the red one. It's the original bit red LED. Okay, bit red LED, and we doing this here. Bit red LED. Skip if bit is 0. Skip if bit is 0. That means the LED is off. That means the LED is off to the switch on LED, correct? If it's clear, then we must switch it on. We must switch it on. Ah, my gosh. We must switch it on. Set bit import C bit red LED. switch the LED on. Correct? And then we must reload the counter. We say load immediate counter with what? With counter startup also. What we talking about? Counter blah blah. Counter. Where is the counter? Counter here and counter there. We must switch it on. Blinky time. It's Blinky time. We must do it. We load it with Blinky time. We must load it with Blinky time. Reload the counter with the 300 millisecond Blinky time. Okay. And then we jump to the Blinky end. Here we are. Blinky end. Double point, and here we have a return. This means return where it come from. And this is the interrupt in the calling upstairs here. So it's open now, the program. That means we must also turn the LED off. Yeah. And reload the register. And we have the second way. Branch equal if the Blinky change. Okay, but this next is we are decrement the counter. If it's not 0, we are not branching, we decrement the counter. This means counter -1. All the loop. We decrement the counter and we jumping to Blinky end. We jump from here to here and return. Okay. If it's null, the counter is over. Blinky change. We must branch equal Blinky change. We jump here. If the LED is clear, if this bit is clear, skip if bit is clear, then it jumps here. It's 0. Set bit blah blah. Load Blinky timer. Jump to the end. If Blinky LED is off, it's here, then we must switch it. No, it's on. Jump to Blinky LED on. Then it's on. No, it's off. It's on or it's off. What we must do here? Blinky LED off, double point. We level it and we say CBE, clear bit immediate, import C, that we know, and the bit number is bit red LED. And this clear the bit, clear the bit clear or null the bit, clear the bit red from the LED. Okay, and important, load immediate the counter from Blinky time. That means reload the counter with the 300 millisecond Blinky time. You see that? And then we need to jump to the end. It's not necessary, but for the understanding, we run into the return. Yeah. We can leave that. But I write it here for you. Jump Blinky and jump to the end, but this must not be here or written. We can do that like this. Yeah. It's only a dummy. Yeah. We store that. And now our Blinky program is finished. What I also must mention is that we have one failure here that's at the assembly time coming out, and it's about the sleep functionality, but I don't remember where it was. It was here around no, initialization. Oh, it means idle mode enable. Yeah, this is one big failure that we must fix, and now the error is fixed. In case of this, is standing in the sleep enable is up here from the here it is, idle mode enable. That means that the sleep can start. If the sleep is enabled, we don't enable it yet at the moment during the cannot step on the machine. I make here a jump to Z, but normally is here a point comma. Yep. We store that at the DOS format. Super. Now there was a mistake with the assembly. I'm doing the wrong. I'm playing the grid all the time in and wondering why I not Blinky. And then I found out there is also a mistake in the program we must fix. We must fix that first. But you can see it's Blinky. In 300 milliseconds, I think so. But if we're doing a second time in, we can also change the off and the on time. Yeah, we can interchange it to make other Blinky, burst Blinky, or faster Blinky, slower Blinky, or it's not easy. It's very easy to implement it now. This is you see the grid. The grid is running, and this Blinky is coming and not coming. Yeah, this is super. Yeah, I'm very happy with this small project. Now you can see the Blinky in this thing. It's super. It's an assembly program with two programs, and two programs are running, the master cycle and the grid and the Blinky. And you can implement all in this calling. All 10 milliseconds will be called your program. Now you can stack it after the Blinky. You can write a second program, a keyboard request or a LCD enabling initialization and whatever. We can do that. If you want, please write in the comment line what you think about this Blinky. And I hope so you have a Windows computer at home that you can also do this, or other computer, Mac is also possible maybe. And we are also have a watch maybe where you can download the AVR Studio from the microchip site. Yes. If you like my channel, please subscribe, and I say thank you for watching.